Welcome to Finite Element Methods. Today we'll be discussing how to formulate a 2D finite element analysis, and we're going to be applying that to unsteady or steady state heat transfer analysis. So let's go back and discuss the background to finite element methods. What is the basis of finite elements? Is the development of approximate solutions to partial differential equations. That is what we want to do. We want to find ways of solving partial differential equations using a systematic approach that is organized, that can be codified into software, and we can then execute this and find the solution to the problem. And that has to be done in systematic problem approach for any general geometry, for any general loading condition, and so forth. So the chief motivation of the previous lectures that we discussed so far is to demonstrate that process, how we get there. So what was the first step? The first step was to derive the partial differential equation for the various physical problems of interest. Then we want to formulate the general behavior of the element. And once I know how the element behaves by approximating the solution over the domain, I can then go ahead and discretize the domain of the structure into elements. We can then go ahead and assemble the stiffness matrix and force vectors, and then solve the algebraic system of equations. In this particular discussion we have today, we're going to address how to approximate the solutions to partial differential equations for 2D finite elements. So let's look at the steps from top to bottom. Step number one is to establish the strong form of the problem and determine the partial differential equation. Step number two is to establish the weak form starting from the strong form. So I have the strong form of the problem, which is really the partial differential equation. And what I want to do, I want to develop the weak form from the strong form. We found that by using the weak form, we can reduce the continuity requirements, and that allows us to be able to approximate the solution to the partial differential equation by ensuring that we can minimize the residual error and making it orthogonal to the weight functions. And we can then integrate that over the domain, and we can then reduce the error in the average sense. Step number three is to take the domain that we have of interest, could be the aircraft, whatever it is, and we want to divide that domain into elements. And we're calling that the mesh generation portion. So I have this 2D, this domain 3D or 2D, and the idea is to break up that domain into subdomain called elements. And what we want to do is find break it down into domain subdomains where the elements are similar to each other in geometry, for example. And I'll show later how to approach it. Then the next step is to determine the element formulation and stiffness and force vector. So what is that about? So what I want to do is to approximate solution over the subdomain. And to do that, I have to formulate the problem so it's in terms of unknown coefficients as the nodal quantities. The approximate function in that way satisfies the essential boundary conditions, and the unknown quantities are then continuous across element boundaries. So that's the way you want to go about that. We'll substitute the approximate function to the weak form and use the weak form to determine the expressions for the stiffness and force vectors. That is the idea. Again, we want to use a weak form Galerkin to approximate the solution over that subdomain. And to do that, we're going to select an approximation that makes sense for the problem. And we're going to do it in such a way that's in terms of nodal unknowns. Remember, when we first started this, we're making it so it's unknown coefficients that had no physical meaning. But now these coefficients do have physical meaning, and it is actually, in fact, the nodal unknowns of the variables of interest. And that by making that happen, what I'm able to do is to determine the stiffness and force vectors. So the column of unknowns is based on those nodal unknowns. And that allows me in step number 5 to then assemble back all the elements together, apply the nodal boundary conditions, It's particularly the essential boundary conditions and the natural boundary conditions, and then that enable us to solve the global system of equations for the unknown nodal quantities, and then I can use that to post-process the results to understand and solve for the flux, stress, strain, and everything else. I want to kind of remind you, we went through these already, but I want to remind you a little bit about the heat transfer boundary value problem. If I have a heat source Q over this volume, we know it has to be balanced by the heat flow per unit area across the surface here. And so therefore I have to have QNdA over that surface, while Q is a heat source or heat sink within that volume, and that has to be equal to each other because there has to be balance of energy there. If I look at the heat flow across the surface, I have the Q that comes across that surface, and Q dot N provides me the normal component of the heat flow, and that's actually a very important quantity that allows us to understand the heat flow coming out of the system. And so, if you recall, for diagonal orthotropic and constant conductivity matrix, and when I say constant conductivity matrix, what I mean is not spatially dependent. The 3D version of the governing equations that we had previously discussed is given by Q plus gradient D gradient T equals 0, and that's in V. And T is the temperature specified on that surface, and Q is the one specified on the natural on the natural boundary condition on this surface right here. So I can use the first law, which is Qn equals the minus D gradient of T transpose N. And you can see here, I can put it all here into this equation. I can plug this into this equation, and that gives me the governing equation for the heat transfer problem here at the bottom. You can see here that that equation is going to have conductivity information, and it has the temperature information. Okay. So with that information, we can now go ahead and continue to work the problem. I have this partial differential equation. I have Q, the heat source or heat sink. T is the temperature, and X, Y, and Z are the different directions the of the system in the Cartesian coordinate system. So this partial differential equation for a complicated domain could be very difficult to solve for temperature. And so we had to find a systematic way of doing that. In 2D, the version from 3D to 2D becomes quite simple in general. Now, instead of a volume, you have a 2D surface, a 2D surface with a bounding contour line. And the equation is going to just turn out to be the same as the one in 3D with the third direction. You can see that here. And this again is for orthotropic and constant conductivity, meaning that the Ks are not spatially dependent. They're constant over space, but they can have a degree of orthotropic behavior. So how we derive the weak form for an unsteady heat transfer problem, which has thickness H. So let's look at that carefully. And to tackle that problem, we first have to start with and let's start with the unsteady heat transfer problems to make it more general. And while I didn't cover that term here, in reality, it's not very difficult to understand that you do have another term that needs to be added. And this term has to do with the specific heat times the density and the time derivative. So what is the first step? This is the differential equation. It's actually a partial differential equation, which now depends on X and Y, but also depends on time. So how do I tackle that? I multiply this equation by the residual and by a weight function. The one thing I want to point out, I want to remind everybody, what is the unknown here, right? So we fully know Q because that's a heat source or heat sink. We know rho, the density. We know C, the specific heat. And we know D, which is the matrix of conductivity here. So that's this matrix. I know the conductivity because I measure it through labs. So the only thing I don't know in this equation is temperature. That's really what I'm after. So I take this equation and multiply by V, integrate it over the domain. And in this case, I'm going to assume that the 3D volume has constant thickness H. And now the only thing that I'm looking at is integrating this over the domain dA. And what is the next step? So I have this equation. I'll multiply V over each of these terms. And now I'm going to be integrating by parts. And I want to spend some time here, teach you how to integrate by parts. In previous problems, when we integrated by parts, it was a line domain. It was not a two-dimensional domain. So let's really understand what is going on here. So this term, I don't want to integrate by parts. There's no derivative on Q. This one here can be left alone. There's nothing really here to integrate by parts since there's only one derivative of t, on t with respect to time. This one has two derivatives with respect to t. So that's the one I'm going to try to work on. V goes on the left-hand side. The gradient dot d gradient t goes on the right-hand side. And what I want to do is I want to remove the gradient here and transfer it here. That's what I want to do. And that allows me to reduce the continuity requirements on T. Once I do that, I then draw an arrow plus and an arrow minus. What you see here is something new. You see this N. The reason we have to talk about N is because when we try to understand what integration by parts means, it means that I'm taking a quantity that's inside the volume and relating it to the quantity that encloses the volume. That's what you're really doing when you integrate by parts. And so what is a quantity that encloses the volume is a surface for a 3D volume, is a contour line for a 2D surface. And so you do need to prescribe what the normal is because as you can see, depending upon where I am in the surface normal changes. And so that information has to be embedded here. As usual, though, the bottom here, this multiplication here at the bottom, goes back into this integral. You can see that there. And the reason is plus is because I have minus here times minus is plus. But everything else is the same. I have this one is this one is that one, and that became plus. And then I have the boundary condition, which is this times that times n, and that's what you see here. And again, the integral now is over the bounding contour line. This integral was over the whole area because that's the quantity we're talking about. It's a volume, but h can factor out since it's constant thickness. Same here. And that's why it's a contour line instead now. But you get the idea. This is the weak form of the problem. And notice how we have weakened the continuity requirements because there's only one derivative on V and one derivative on T. And previously I had two derivatives of on T. So I have gotten there. That's a weak form of the problem. Notice how D gradient T is Q. I discussed that here. D gradient T is Q, right? We discussed also that here. Q is D gradient T. And yeah, so this is really the heat flux right here. So let's look at the weak form a little further. I'm going to take this equation and paste it here to fully understand what is going on. And before I do that, what I want to do is I want to take this surface and break it up into two, right? So I want to break it into the part that has to do with essential boundary conditions, the part that has to do with heat flux, the natural boundary conditions. So this equation, I'm going to break it up and put it nicely here. You can see that that's what I've done. Each of these terms have their own integral. That's fine. We don't have to do that, but that's what I did. So I distributed the integrals to each of these terms here But now what I want to do is focus on this term, and I will break it up into two. So I broke it up into the part where essential boundary conditions are specified and the part where natural boundary conditions are specified. So you can break up the integral anywhere you want and however you want. So I just broke it up in a smart way. What we notice here is that um, the surface, the total surface enclosed in the volume, or in this case, it's a contour line because it's the area that I'm integrating against, that the contour line is made up of ST and the union with SQ. So going back here, ST is from here to here, and then SQ is from here to here, right? And so what we notice here is that this right here is QN, and that's typically prescribed. You know what the heat flux is. So QN, we can just put as Q bar. And that turns out to be this right here. Every other term shows up just like you see it. And here, I'm going to just transfer this term here and just say that this is zero because that is the boundary where the essential boundary conditions are specified. And if that's where the boundary condition is specified, then this V has to be zero. So this whole thing goes to zero, and we don't have to worry about this term. Because the homogeneous boundary conditions that I use for my trial functions have to vanish where essential boundary conditions are satisfied. And V is always selected to be the trial function, and the trial function has to be zero by definition where the boundary conditions are specified. Hmm. So the weak form becomes this equation right here. And we already discussed this zero, but this is what we get. So what is the admissible requirements on T? That's admissibility requirements on T. The gradient of T has to be finite, that's for sure. And the essential boundary conditions are given by specifying T. And what does that mean? That T, the temperature must be continuous across element boundaries. That has to be the case. So we could discretize the domain, and we know this is a weak form of the problem. We can discretize the 2D domain using 2D elements and 3D domains using 3D elements. So let's look at how you will go about using triangular elements. You can see here a domain in example number 1, and you can see triangles are being used to subdivide to divide the domain into subdomains. And yeah, that's fairly clear that that's what's going on. And you can see that a single element here is this triangle. That triangle is a finite element. Why is it called finite element? Because in reality, there's infinite number of elements, but I've divided the domain in pieces and into finite number of pieces. This subdomain is called finite element. And this element or this subdomain has three nodes that provide the boundary for that triangular element. In example number 2, you can see a domain of some sort of pin joint and how this structure has been subdivided into multiple elements all across using triangular elements. In example number 3, you see a plate with a circular hole, and you can also see triangular elements being used everywhere to divide the domain. And what is my goal by dividing the domain? Is to solve the partial differential equation over this subdomain and then be able to assemble all the elements together into a sensical solution. So triangular elements are quite popular. There's nothing wrong about them. They can do a fairly good job in general. But I'll discuss later the limitations you may find. So I want to use the weak form Galerkin, right? That's the goal. We developed the weak form here, right? And I want to find a way of approximating the solution for temperature over a subdomain. And here I'm going to use an element, right? So let's try to do that. How can we accomplish that? So for the weak form Galerkin, we need to choose an approximation function. And I'm going to choose in 2D for triangular element. I'm going to choose, so this is what the approximation function could look like, right? The temperature has to be a function of x and y so that it can vary in the x and y direction. Here I have these coefficients that are unknown, and I know I'm going to have a bunch of terms, 1, x squared plus y squared, and so forth. But for linear triangular element, I have three nodes, right? So we have three nodes for linear triangular element. And so I have to have three unknowns. And so it makes sense that I stopped here, right? Because I have three nodal unknowns. Well, I really want to have three nodal unknowns. So these have to be the only ones I consider. So the lowest polynomial in 2D looks like is this amount. But when I go to a linear tetrahedron in 3D, I'll have four nodal unknowns, and I have to add z there, right? Um, there are a minimal number of convergence requirements for 2D and 3D, generally speaking, and then that needs to be considered. So let's look at 2D triangle element. We want the temperature to be T1 times N1 plus T2 times N2 plus T3 times N3. And the nodal unknowns here are going to be T1, T2, and T3. And we have to come up with these polynomials for N1, N2, and N3. This is a better way to approximate the solution to the problem because now T1, T2, T3 are the nodal unknowns at each of these nodes. You can see here that you have three unknowns here, but these unknown coefficients have no physical meaning, and that's why we're trying to reformulate the approximate function in a way that's clearly understood. So here you can see that I have t1 times n1 plus t2 times n2 plus t3 times n3, and what I really want to do is when I plug in x1 and y1 here, I want n1 to be 0, sorry, 1, and then T1 to show up as a value there. I also want to do the fact that when I put X2 and Y2, N1 is 0 here at this node, N3 is 0 at this node, but the N2 is 1 at this node, and so I get the value of T2. It will return that value. At node number 3, I want to be able to plug in X3 and Y3 and then return the value of T3 at this node. So that shape function has to be 1 at this node, 0 here, and 0 here. So something to consider there because we need to use as a property moving forward somehow to come up with the shape functions or the trial functions, right? Again, the unknowns here is the nodal coefficients. That's what matters here. And then we have to come up with the shape functions in such a way that that occurs, with what I just talked about, right? Um, For the 3D case, you're going to have four shape functions, not three, four nodal coefficients, one per node, because those are the temperatures that are not known at each of these nodes. In 2D, we have the following polynomial approximation. So let's look at 2D. And I'm going to use this at a counterclockwise direction. I think that's important when you work two-dimensional problems. So to specify what direction you're going to start working the problem. Um, but in general, what we have is I have an approximation function here that I want to use, but I want to relate that to the nodal unknowns. And so to do that, I know that at T1, I should get T1 when I plug in X equals X1 and Y equals Y1. I should be able to get T1. And that gives me A plus BX1 plus CY1 and so forth for T2 and T3. That's what I'll get. I'll get the temperature 2 and temperature 3 in this manner. I can rearrange this in this format. And really what I'm after is I'm trying to figure out what does my approximation function look like? So I'm really trying to solve for A, B, and C, given that I know X1 and Y1. X2 and Y2, X3 and Y3. Because when you look at this problem, you do know the nodal coordinates of that triangular element. So just to make sure you understand, we know X1, Y1, X2, Y2, and X3 and Y3. We know them. And I don't know the temperatures, but we can presume we know them at the nodal locations. and try to figure out what A, B, and C are in terms of T1 and T2 and T3. Because with that information, I can try to figure out what my shape functions look like. So in this step, what I'm trying to do is write these three equations in matrix format in a simple way to understand. You can see that the first equation is exactly that equation. So first row times column, right? So 1 times A is that, plus B times X1 is that, plus C times Y1 is that. So clear there, and that's T1. The second equation is also clear, and the third equation is also clear. So now I can go ahead and invert this, and this is what I get. And this will give me a bunch of constants. And how can I determine the shape functions, right? So how do we do that? So tx comma y is a plus bx plus cy equals, and then I have this 1xy. You can see that this equation is exactly that row times that column. That's exactly what I get. And so now my next step is to figure out how to find the solution. Well, I know the solution because A, B, and C were found taking the C inverse times this column vector. Well, guess what? I know A, B, C from this equation. So plug that in here. And so now if I multiply this row times C bold inverse, that should give me the shape functions that I'm looking for. So the approximate solution to temperature is the shape functions times this column vector of unknowns. And now I'm ready to then substitute these approximation functions. But let me just back up a little bit to remind you what we've done. We came up with the approximation function that looks like this, and that makes sense. I should have three unknowns because I have three nodal unknowns. And I want to relate that to the nodal values. And to do that, I know that at x1 and y1, the temperature is T1 and so forth. So I can put that in this matrix like that, solve for A, B, and C by inverting that matrix. So I get this. I call this C bold inverse. And yeah, that's how you find A, B, and C in terms of T1, T2, and T3. And then I know that the temperature is A plus BX plus CY. Column vector times row vector should give me that. But I found A and B and C, and that's C inverse times this. And I can just plug it in here. And if I multiply this row vector times C bold inverse, right here, this multiplication gives me the shape functions I'm looking for. And the thing I want to make sure is clear to everyone here is that if you want to really learn how this is done, you should do it yourself by hand. Otherwise, you're going to struggle in understanding these ideas. But if I go ahead and multiply everything out, I multiply everything out and I conduct this operation here, you'll find that the shape function is basically this equation that looks quite complicated. And you can see here that the shape function depends on the nodal coordinates, as you can see. And then x and y are varying within the triangle. A is the area of the triangle, which is given by this equation. But you get three shape functions, and they look quite complicated, of course. And I invite you to try and see if you can find this. If you do, just comment below in the video and say I did it and I got the same answer. But I think you're going to find if you did it in Mathematica, which is what I suggest you do, don't do it by hand, you'll find that these are the shape functions for a general triangle with general nodal coordinates in the 2D domain. You could check this very quickly to see if it works out, but we won't do it here because it will take a while to really work it out. And we want to really focus on the learning experience on the top level view. So these shape functions are actually quite amazing. If you were to plug in x1 and y1 here, surprisingly, you will get one here. And this will also be 0 at nodes 2 and 3. Shape function 2 will be 1 at this node, x2 and y2, but it will be 0 at the other two nodes, and so forth. So if you're to plot it, you will find this. You will find that shape function 1 has a height of 1, 0 here and 0 here, and so forth for shape functions 2 and 3. So it works out very nicely. I invite you to try it out. It also satisfies the partition unity If you added these three equations, you will get the n1 plus n2 plus n3 is 1. Very powerful idea. So yeah, here's what I'm showing you. I'm showing the n1 plus n2 plus n3 is 1. Remember, the n1 and n2 and n3 in the weak form Galerkin are the basis functions, the trial functions. And those are the ones that uh, have to satisfy the homogeneous boundary conditions. We discussed that. And in this case, each of these shape functions is 1 at the corresponding node, but 0 at the other nodes. And then the summation of these shape functions is 1, which is quite powerful. So why is it important that the shape functions satisfy partition unity? It has to satisfy because say the temperature here is T naught, the temperature here is T naught, the temperature T naught here at this node is T naught, right? Um, then any value in the center here should be T naught then. So let's plug in what the approximation function looks like, right? I have T equals T1 times N1 plus T2 times N2 plus T3 times N3. And since Ti in every single node has T naught, it factors out. But obviously, the temperature at any point in between has to be T naught, has to be. So the left hand side is T naught, the right hand side has a T naught. That cancels out. So the shape functions become 1. Adding them. And so that makes sense. It makes sense that has to happen. And that's a necessary condition to be able to represent a uniform temperature state. The second thing that I want to point out is that we have a conforming interpolation, meaning if I have two elements, they share an edge. And at this edge, I will expect that this element and this element at that edge, they there's a conforming interpolation at this edge, meaning the interpolation functions going across this element boundary are the same for either side. The temperature along the edge only depends on the nodal values here and here. And so for global continuity, elements have to be conforming. And that means that the temperature approximation must be continuous across element boundaries. So if that temperature for this element and the temperature for this element at uh, this node is shared, then those temperatures have to be equal, and therefore they share the same interpolation across its edge. So these two properties, very important. Let's look at this a little more. So we chose an approximation function of the form of a plus a gradient of some kind, where here you have that this represents a constant temperature, so I can get to that. B equals 0, C equals 0 gives me that. And then I can represent the gradient of T, which allows me to give me a constant gradient across a triangular element. In the weak form, we need to calculate the gradient of temperature. I mean, that's one of the things that needs to be done. But we have demonstrated that is suitable approximation. We've been able to show that the triangular element is excellent because it can represent a constant temperature state and it can also represent a constant temperature gradient. That's an important factor in what we're talking about here. And you can see that this temperature approximation does that. We can represent a constant temperature and also a constant gradient. So very nice. Together, I and 2I, these two conditions together are called the so-called completeness requirements. So conformity plus completeness equals convergence. Meaning if I have if I refine the mesh, I have more nodes, I'll get a better approximation. As long as I mesh it more, I should expect them reaching the asymptote, and I'm getting better at getting to the exact solution. I can add more terms if I want it, but they're not guaranteed for convergence. Um, I don't need them. I just have to just increase the number of elements. That's one approach. I can add additional terms if we want, um, but we cannot just skip these terms. We have to keep these linear terms and then add more terms. So these are the bonus terms, right? And just to bring you back to what that meant, right? These are the minimum number of terms I need to represent constant temperature, to represent a constant gradient for temperature, but these ones are added bonus. I cannot just keep the constant temperature term and the gradient term because then I will never be able to achieve convergence. So let's try to use the weak form Galerkin. Now I'm ready to go. Um, so I have the weak form here. My goal is to approximate the temperature using the shape functions. And I'm going to use separation variables again, where the shape functions only depend on x and y, while the temperature depends on t. And by doing the separation variables, then I can use finite difference to time march the solution, and I can use the shape functions to try to approximate solution over the spatial domain. And so if I look at t dot, which is required by this equation, that's the derivative of t respect to time. And so this is the only thing that depends on time. So that's why I get m bold times d dot, t dot. You also see that I have to substitute v by n bold transpose. I've done that here. You can see that for v, I put n bold transpose. And then d bold is this one here. Gradient of t is just essentially the gradient of n bold times t bold. That's exactly what you see here. And then I have the next term. So I have rho c, and then v is m bold transpose. T dot, you can see here that T dot is M bold times T bold dot. That's exactly what you see here. And then I have HDA over there. This V here is an error, so that V should not be there. I'm sorry about that. Minus the integral, and then for V, again, M bold transpose, Q stays there, and then here again, V is M bold transpose. And these on the surface, while these inside the volume. Very important distinction. Now I can take t bold outside of these integrals, and you can see here I've done that. And then these become the forcing functions in heat transfer. So these can go to the right hand side, and this is what I get. So this is the equation I get. That's the element formulation for the problem. And everything here is known. I know this integral. I know this integral. I know this integral. I don't know t bold. That's what I want to find. But I'm able to use finite element discretization to take care of the spatial domain, and now everything's in terms of the time domain. I can further look at what the gradient of n bold looks like. I think it's important to discuss what that looks like. So the gradient of n bold is really this partial of x and partial of y, n1, n2, and n3. So that's how you take the gradient. It's very simple. You multiply this by that, and that gives you the first row. Multiply this by that, and you get that second row. So 2 by 3, you can see it's 2 rows by 3 columns. So we get 3 equations and 3 unknowns in terms of the temperature. You can see B bold transpose becomes a 3 by 2. D bold is 2 by 2 because it's a 2-dimensional problem. You can see that here. B bold is 2 by 3. So therefore, this whole thing gives you 3 by 3. That makes sense. Everything else is the same as I showed you here, but I want to discuss the size of the matrices and how to calculate that gradient of M bold, so it's clear to you how to do that. Because you may have seen the gradient of temperature, and that's easy, but what's the gradient of a row vector? And so I'm trying to kind of discuss what that looks like in case you've never seen it. And again, I really encourage you to pause the video. Make sure you're deriving the equations from scratch, because if you don't, you're going to have some difficulty understanding the ideas. So for quadrilateral elements, the same idea applies. If you have a domain that looks like this one, I can divide the domain into quadrilateral elements, and you can see a triangular elements. You can mix them up. And the quadrilateral elements can have arbitrary locations for their coordinates. Um, and it's the same idea where I want to choose an approximation function for this problem. And so because there's four unknowns here at the nodes, I think what makes sense is to choose a fourth order um, approximation here. And you can see I have a plus bx plus cy plus dxy. And I don't mean fourth order polynomial, but a four term polynomial equation. You can see here that I need four unknowns to enable four nodal unknowns. And so what do I really want? I want to be able to write this equation here so I know n1, n2, n3, and 4, and want to find them in such a manner that it satisfies partition unity and also the Kronecker delta property. Once again, the temperature at this node should be equal to T1. I want this to be 1 at this node, but 0 at all the other nodes. I want N2, N3, and 4 to also be 0 at node number 1, so that when I plug in X1 and Y1 here, I get temperature 1. And that's all I get, times 1 here for N1. And we can do that following the same procedure we talked about. So when I look at the approximation function, you may ask me why we selected x, y. Why didn't select x squared and y squared as a fourth term? Well, because if I chose x squared and y squared, I'm biasing the solution too much either on x or y. And that's not acceptable. I want something that's unbiased to both x and y. So an acceptable one is xy. So how do you determine which ones you should be selecting to be unbiased? The Pascal triangle can be very useful on how to build that. So to remind you, the Pascal triangle has these exponents here. So here you have 1, x to the power 1, y to the power 1. Here you have x to the power 2, xy, y to the power 2, and then so forth. So this is how you basically determine. So how do I derive this Pascal triangle? So you take the outer row, 1 x squared x cubed, and you keep increasing that linearly up. 1 y squared y cubed y fourth and so forth. And then how you fill out the spaces. So here is this is going to be this times that is this times that is yeah. So in essence now you have to increase the order by 1. So this times that is this times that is this, and then you just keep doing it. And you fill everything up until um, you have the whole Pascal triangle filled up. The exponents have to add up to 2 in every row. So here you have 2, 1 plus 1 is 2. Here you have 2. Here you have to have 3. Here is 2 plus 1 is 3, and so forth. So every row will increase by 1. So that's how I use Pascal triangle. And so for triangular element, I need 3. So that means I have to stop here. For quadrilateral element, linear one I'm using, bilinear, we call it. Um, I don't want to go biased, so I'll just draw a a line around this 4 because that provides a unbiased approach for this approximation function. So this is a great approximation function, and notice that we have now added this bilinear term, also called the surplus term, which is required for the quadrilateral element because I have 4 unknowns, and so I have to get there somehow. So I'm going to use the same procedure. I have 4 nodes for which the temperatures are known or not known, but I want to write A, B, C, and D in terms of T1, T2, T3, and T4. To do that, I can write each of these equations into this system of equations. I can invert A, B, C, D like this. And again, I'm able to now find A, B, C, and D in terms of T bold. Once I have that, I'm ready to plug in A, B, C, D for C bold inverse times T bold. These multiplications times that gives me a row of shape functions times T bold. And this right here is M bold times T bold. M bold equals 1xy and xy. So I'm able to multiply this times C inverse, and I'll be able to get the shape functions that I need. So the rectangular element, so if you just look at a very simple rectangle, but if you use a just general quadrilateral, it's quite an expression that's very hard to manipulate. What you see here is that N1, N2, and N3 for look like this for a rectangular element. We can check it. So that's why I did this particular example. So if I choose x0 and y0, I get a shape function of 1 here. But I should get 0 here, which I do. I should get 0 here, which I do. And I should get 0, which I do. We can also check this one here. What happens there? So that's an x of L and a y of W. That gives me exactly 1. But you will see that this one will be 0 everywhere else, and those three shape functions will be 0 at this particular node, 3. So it works out. You can see that it works out, and I invite you to add them up all, and you'll find that they equal to 1. Because of the same idea that if this node and this node and this node and this node have the same temperature, everywhere in between should be the same temperature, which forces you to have N1 plus N2 plus N3 plus N4 to be equal to 1. So shift functions do satisfy the partition unity, like I discussed before, just right now. And then it satisfies the Kronecker delta property that I also discussed. So for the 2D bilinear quadrilateral element formulation, the only thing now is I have this extra shape function, but everything else is the same. And I just get a 4 by 2, 2 by 2, 2 by 4, and so forth. It's the same formulation, but now it's just an extra node. But the procedure is the same, nothing changes. Everything here, these integrals can be calculated straightforward manner, and that will allow us to find an expression for the general element formulation. So that's how you do it for the global coordinate system, how you go about that. And I do want to point out there's other partial differential equations that are quite complex, but you can use the same equations I was showing today, just change the variables as you see here to recover a particular physics. For example, heat transfer problems will use temperature as a variable of interest, and the data you need is thermal conductance, which are the Ks, right? The conductivity. And you can look at flow, a torsion, a deflection of membranes, inviscid flow, and electrostatics. I invite you to pause the video and kind of look at this table and get familiar to the kinds of physics you could encounter and how powerful that can be for solving a lot of different problems in continuum mechanics, but also in other areas of expertise. Now, I want to point out that what we've done is actually not very useful the way I presented it. And let's think about that for a second. You can see the shape functions will be different for every single element because it's very unlikely the elements will look like so nice like a quadrilateral. Every element is going to have a different shape, most likely, as you saw here. Every element has a different shape, different coordinates. So finding the shape functions for every element will be very intractable if I have to do it for million degrees of freedom. Secondly, if I have to now integrate over the domain and that domain is irregular in shape, that is a problem too. And yeah, it's just not convenient. So we had to find a different way of doing it. And that's what the next lecture is about. So I hope you enjoyed today's lecture. It provides motivation for what we're doing, and that it builds a foundation for the very next lecture, which is to find a solution to the problem I just mentioned, which is that the shape functions for every element is different. Integrating over the domain for irregular shaped elements can be also challenging. So how do I address that? How do I come up with an approach? That's the subject of the following lecture. Thank you so much. You have a great day, and I hope you learned something great today. Have a beautiful day.